right, we have been talking about reaction kinetics, which is how fast reactions happen and what their mechanisms are. We started with what we're going to call a substitution reaction, where we've replaced a leaving group, in this case iodide, with a nucleophile, Cn-, and the products are substitution products. We've swapped out what used to be attached to the carbon for something else. And we'll have a lot to say about what makes these reactions favorable. In particular, though, if the bonds you make are more stable than the bonds you break, that's the driving force for going forward, but that's an issue of thermodynamics. The issue of how and when and how fast is an issue of kinetics. So we envisioned at least a couple of mechanistic hypotheses. One wherein we made the carbon-carbon bond first to get some intermediate with 5 bonds to carbon, and that made us a little uncomfortable because we've been taught not to have 5 bonds to carbon, but we're just generating hypotheses here. So we'll talk about what the evidence suggests later. And then we might break the carbon iodide bond to give us products. We talked about how along the reaction pathway, you pass through transition states as you go from one energy minimum to another. Going from something that's neutral to something that has a negative charge on this carbon probably means going uphill in energy. In general, steps that involve a lot of bond breaking are uphill. This step only involves mostly bond making, but it takes energy to rearrange this carbon from being sp3 hybridized to being something like this intermediate. And so that can account for how high up in energy we go. The intermediate is presumably some energy minimum, and then there's a second transition state that involves the iodide leaving. The activation energy for the first step is the energy difference between our starting materials in the first transition state. And you can see, we'll call that activation energy for step 1. You can see that's a lot bigger than the activation energy for step 2. At least the way we're thinking about this, the idea is once you have a high energy intermediate, releasing that leaving group is probably not very costly. So you expect the rate of the reaction to depend on this first step. We'll call that the rate determining step. Yeah?
How often is it that the first step is the rate determining step?
How often is it that the first step is the rate determining step? I mean, in 351, perhaps a lot. In 352, not so much. When you get into reactions that need catalysis, where proton transfer is involved, those are often first steps, but they're pretty fast. So sometimes. Okay. Then we talked about another possibility in which we just break the carbon iodide bond to get a carbocation intermediate, and then we make the carbon-carbon bond in the next step. So it's kind of like mechanistic hypothesis number 1, only we've switched which steps happen first. We break the carbon iodide bond. The transition state here involves iodide, the carbon iodide bond getting bigger and longer and longer and longer until iodide's mostly gone. And then the transition state for the second involves Cn- coming in and forming the bond. And we similarly envisioned that in this 2-step reaction, breaking this bond should be uphill in energy. The intermediate is higher in energy than the starting material. I don't know what all of that means. Intermediate I. And this activation energy for the first step is larger than the activation energy for the second step. This makes sense from our bond breaking versus bond forming perspective. In the first step, you're mostly breaking a bond. In the second step, you're mostly forming a bond. And so we would expect the first step to be the rate determining step. Okay, so that's hypothesis 2. We're going to generate one more. This will be mechanistic hypothesis 3. And this will be that we make the new carbon-carbon bond at the same time as we break the carbon iodide bond. And one word we have for reactions, or rather a reaction in which multiple bonds are formed and broken at the same time, we'll call that concerted. They are forming and breaking in concert together, and so you might envision some kind of reaction mechanism like this, in which we will have the carbon attack the other carbon as the leaving group leaves. Our transition state, and we'll go in a single step from starting materials to products. And the transition state presumably would look a little bit like that intermediate we had for mechanistic hypothesis 1, in the sense that we would expect to have some kind of transition state that looked like this, with a bond between carbon and carbon partially formed, and a bond between carbon and iodide partially broken. And you can see that this hypothesis differs only subtly from the first mechanistic hypothesis. In the first hypothesis, we're saying this is an intermediate. For our third hypothesis, we're saying that's not an intermediate, it's a transition state. The difference between an intermediate and a transition state is intermediates occupy energy minima. They can be observed. They have a lifetime. Transition states generally can't be observed. Their lifetime is about as long as it takes a bond to vibrate, which is really, really, really fast, really, really, really short. So we would predict that for the mechanistic hypothesis number 3, that we would go from starting materials to products. But we would do so, if this is energy, we would do so over a single transition state. All right, and in each case, the starting materials and the products are the same. The energy difference between starting materials and products is the same, but the energy diagram of how the reaction happens is different, and the steps are different. Okay, questions about these 3 hypotheses? Yeah?
Yeah, so the other 2 hypotheses, the reaction we see was also exothermic, so it doesn't matter which one it is. If it's going to be exothermic for one hypothesis, it's going to be exothermic for all hypotheses.
Right, whether or not it's exo or endothermic, and that refers really to whether it's favorable downhill in energy or uphill in energy is endothermic. That isn't an issue of kinetics. So if I had drawn all of these absolutely correctly, the energy difference between starting materials and products, and this is downhill in energy, it's exothermic, that energy difference would be the same for each of the mechanisms. Now, you could say, well then, does it matter which one it is? And we're going to see that it does, because depending on which, we're going to try to think about some experiments we could do to distinguish between one mechanism versus the other. And we're going to see that the products might actually be different in certain situations. I've deliberately chosen a simple example where you can't tell, but we're going to talk about experiments that you could do to demonstrate what the mechanism is. Yeah?
Maybe you just said this and I blanked out, but which one is most observed? Which one is most typically observed in nature?
You want to know the answer yet, and answer already, and I'm declining to tell you the answer because we're going to talk about experiments that you could use to verify one versus the other. All right? Okay, let's talk about how you can tell one mechanism from another. One of the easiest ways to do this is to do experiments where you measure the rate of the reaction, and you see how the rate of the reaction depends on the concentrations of the starting materials. So you maybe know a little bit about rate laws from general chemistry. Have you learned how to write a rate law for a single step of a reaction? Okay, some of you are nodding, others of you have already filed that in the, have already dumped that to long-term or non-existent memory. We're going to dig it out and just review it briefly. It's not that bad. For a reaction like this, where the first step is what we'll call the rate determining step, or RDS, we look at what things are involved in that rate determining step, and we will say that the rate of appearance of product, we'll just call it rate, but for those of you that care, that's D, change in concentration of product versus time. If you want to ignore that and pretend that calculus doesn't exist, that's totally fine. We will say that the rate equals some rate constant times the concentrations of the molecules that are involved in the rate determining step. So in this case, we would see that both CN- and methyl iodide are involved in that first rate determining step. Okay, so let's talk about how you might interrogate whether this is true or not. I don't actually know that it's worth spending a lot of time on mechanistic hypothesis 1 because that's not the right one. I will say that you could probably do some kinetic experiments to demonstrate one versus the other. If you do calculations though, this structure is not an energy minimum, it's an energy maximum. So, and we've learned not to draw intermediates or starting materials or products where carbon has 5 bonds. And the reason for that is carbon is too small to form strong bonds with that many things. Another reason for that is carbon comes with 4 atomic orbitals and so can form 4 bonding orbitals and 4 anti-bonding orbitals. Presumably if you bonded to more than 4 things, you got to start filling anti-bonding orbitals and that might not be great. In any case, we're going to rule out mechanism 1 because of the Texas carbon. Okay. Yes?
Can we always rule out something that can't bond to more than 4?
Yeah, for carbon, if it's bonded to more than 4 things, you probably drawn the wrong mechanism. There's a whole subfield of organic chemistry where people like to demonstrate that rules of thumb aren't universally applicable, and so there's always you can always find weird exceptions to things, but we're not gonna worry about that. Yeah, Texas carbon is a dead giveaway for a wrong answer. Okay, so, but the idea of thinking about what the rate law would be and comparing it is going to be useful for distinguishing between mechanistic hypothesis 2 versus 3. So we would predict for the rate determining step for hypothesis number 2 that the rate would only depend on the concentration of methyl iodide because that's the only thing that's involved in the rate determining step. And in contrast, if we were to go down here where 2 things are involved in the rate determining step, we would predict that the rate would depend on both the concentration of the nucleophile and the methyl iodide. All right, how do we measure rate? You need a way to detect the appearance of one product versus another. Sometimes you can do this through chromatography, gas chromatography, or HPLC, or NMR, which we'll learn about later. The exact experimental technique isn't important. But if you could imagine measuring the rate of a reaction and varying the concentration of methyl iodide, you would expect, if this mechanism were actually operative here, you would expect the rate to increase linearly as you increase the concentration of methyl iodide. By the way, if the rate increases linearly with concentration, we will say that the reaction is first order in methyl iodide. Another way of thinking about that is that the exponent on the concentration term is 1, or that only one molecule methyl iodide is involved in the rate determining step. Yeah?
So even though it goes up linearly with the rate, if you measure the reaction like over time, like concentration over time, that'll be exponential, right?
So let's see. The exponential part actually comes from, right, if you were to, sorry, it took me a minute. We're plotting rate of the reaction versus concentration. However, if you wanted to plot the concentration of a starting material versus time in this reaction, that would be exponential decay. There's just a really quick calculus / differential equation you can use to show that. We won't worry about that, but you probably have seen something like that in the class where the concentration of something as a function of time is equal to some pre-exponential factor times the number e to the minus kt. Don't worry about, you won't be doing that kind of math here. Yeah.
So the exponential on the concentration, is that also correlated to how many groups need to be involved to react?
Yeah, so what we just did, this would be true for this simple reaction mechanism. If we made it more complicated, the concentration versus time plot would be different. Yeah, and what we're doing here are very simple rate laws. If you want to do complicated rate laws, you should come take my Chemistry 552 class in the fall. Actually, I'm not teaching anymore in the fall. I'll be with Dr. S, but that'll be even better than me. So nobody's going to do it. Okay, so for this reaction, in contrast, if we had varied the concentration of Cn minus and measured the rate, what we might see is that the rate is basically independent of the concentration of Cn minus. And so we would say that the reaction is 0 order in Cn minus. And so technically you could write the rate law if you wanted to. You could write it like this with methyl iodide raised to the power of 1 and Cn minus raised to the power of 0. Okay, and because this reaction only involves one molecule in the rate determining step, we would say that this is a unimolecular reaction. At this stage, people often ask, how can the reaction rate be truly independent of the concentration of Cn minus? Because if you don't have any Cn minus there, the reaction isn't going to happen. And that's right. The rate law, the real rate law is more complicated than this, but at large enough concentrations of Cn minus, it simplifies to this. So we're going to be working in a world where if we want a reaction to happen, we're going to use a fair amount of both alkyl halide and nucleophile. So we're not going to worry about that limiting case when what happens when Cn minus is really low. Yeah.
Use titration to find the rates.
How could you find the rate titration? You would need some way to detect the concentration of product or the disappearance of starting material as a function of time. So that's really an analytical chemistry question. You can do that sometimes with absorbance. You can do that through a technique called NMR, nuclear magnetic resonance, which allows you to see evidence for a specific structure, and you watch it go away with time. There are other spectroscopic techniques, and it sort of depends on how fast the reaction is for what kind of technique you need to use. Yeah?
If something was going to be second order in whatever molecule it is, would that look like an exponential curve?
If it were going to be second order in something, yeah. So hypothetically, if you want, if something were, if a reaction were, if a reaction were second order in molecule A, if you plotted rate versus concentration of A, you would see a parabola, half of a parabola really, because you can't have negative concentration. And then you could plot, well, what's going on there? Sorry. you could plot rate versus A squared, and that would be linear. Yeah, a lot of different things, yeah.
Sorry, I think I missed something, but how did you graph that initial CH3I rate? Did you just know because it's a curve that it's going to be a straight line and that's all that matters? That's all you know?
So what you would do is you'd measure the rate at various starting concentrations of methyl iodide, and then you would plot the rate versus methyl iodide concentration. You do curve fitting to determine what type of equation it best fits to, and if it's linear, you say it's first order. Does that answer your question? No?
I'm just like, did you do that just now?
I didn't measure anything just now. I'm showing you what you would observe for this hypothesis if it were
Do we need to
true.
do that if we're trying to figure out something like this? Or just a rough estimate about the rate versus the rate would be?
So I suppose, I mean, you're actually now pushing me on what kind of test question you can expect. I don't know that I've written one on this before, but it's sounding intriguing. Oh, no. No, I suppose I could say, I plotted rate versus this concentration. What do you think? Is that first order? Can you tell if a curve is linear versus not? Yeah. Yeah.
I thought I remember from Q-6 that the rate by the concentration, if it's natural log of concentration, then it's linear, then it's the first order, and if it's 1 over concentration and it's linear, then it's second.
So yeah, there's a question about natural logs and stuff. I think probably you're thinking about a relationship between rate constant and concentration. I could be wrong, and if you want to know more, it would just take me a minute to write out the rate laws, but that's already more mathy than we want to do. Okay. So if the second mechanism were right, we would expect to see a reaction that was both first order in nucleophile, or Cn minus, and first order in methyl iodide. And so if you did a similar experiment as we've talked about above and plotted the rate versus concentration of methyl iodide, you would observe a linear dependence of rate on concentration, whereas if you similarly, if you varied the concentration of Cn minus and compared it to rate, this time you'll also see a linear dependence. And if you do these two experiments, you can get an idea not only of what the dependence of rate on these concentrations is, but you can actually calculate what the rate constant is. And the rate constant is actually related to this energy difference here through stuff you don't want to know. But basically, the rate is faster, rate constant is higher if this energy difference is lower. Okay. Right, so that's one experiment we can do to distinguish between which of the two mechanisms is operative here. Questions so far? Yeah?
Yeah, so we've seen the two hypothetical graphs of what it look like. Which one is
Which one is it? I'm still holding out on that. For this particular example, if we did the experiment, we would observe option 3. Okay? But there are cases where instead you observe option 2. And so aside from doing the kinetic experiments, I want to talk about some other ways we can determine what the mechanism was. We'll also talk about factors that favor one mechanism over the other, all right? But you will come to hate these two mechanistic hypotheses, and you will hate them with reference to the sort of overall name we will give them. This reaction that is only first order in methyl iodide, we're going to call a nucleophilic substitution reaction that is unimolecular, because there's only one concentration term in the rate law. So that's S, substitution, subscripted N for nucleophilic. I don't know why it has to be subscripted, and in fact, I don't care. And then 1 for unimolecular. This is an SN1 mechanism. And when you say an SN1 mechanism, you're implying all of this that we've talked about. In contrast, what we will talk about here, see if you can guess it, SN2, yep. So you will come to hate these because you're going to be worried about whether a mechanism is SN1 versus SN2. And we need to continue to talk about ways that you can tell experimentally, and then as you're answering questions and you have an idea of what the mechanism is, how you can show products that are consistent with that mechanism. So let's start with the SN1 reaction, and I'll just insert some stuff here. Suppose that a reaction proceeded via an SN1 mechanism. So I'm going to show you some alkyl halide. We've got a leaving group here. And we'll use a nucleophile. Let's just use water as a nucleophile. All right, and let's just suppose that the reaction mechanism is SN1. So we can draw the SN1 mechanism. That involves the leaving group leaving first. And then you get a carbocationic intermediate. Now, notice we started out, is that starting material chiral or not chiral? Chiral. Where's the stereocenter? Right there. That's helpful. Right there. Last summer we went on vacation to Driggs, Idaho with my brother-in-law and his family, and he has a little 2-year-old and named Drake, and Drake wanted cereal, and he had already dumped out a whole bowl of cereal. He wasn't actually interested in eating it, so his dad was ignoring him. But Drake thought that the only possible reason that his dad would not be giving him cereal is that his dad did not know where the cereal was. So he stands in the pantry, "Daddo, cereal right there." Right there. So, right there, yeah. Right there is the stereo center. Okay. Now, we would have in a second step, the nucleophile attack the carbocation. And then we would get something like this. Now, let's consider the geometry of this intermediate. That intermediate carbocation, the carbon that's right there, is sp2 hybridized, trigonal planar, and the LUMO is what? It's that empty p orbital. And if we were to, from our perspective, looking down at this carbocation from above, that empty p orbital would look something like this. One lobe above the plane of the page, and then a node in the plane of the page, and then below is another lobe with opposite wave function sign. We could draw this from the side if we wanted to. We'll draw a methyl group coming out at us, hydrogen going back into the plane of the page, positive charge on that carbon. From the side, yeah, we're going to see something like this. So which lobe of the p orbital is that nucleophile going to attack? Right there. The yellow one, the pink one, well, both are options, right? And this intermediate is flat. So, and the faces of that intermediate are identical. So they both have to be attacked at similar rates. So we can attack from above or below. If we attack from above, we get this product. If we attack from below, we get this one. What is the relationship between those two products? Oh, they are stereoisomers, right? Stereoisomers, yes. What kind of stereoisomer? Enantiomer. Oh, yes. We got some work to do then. These two are mirror images of each other. You can tell because they have only one stereocenter, and that stereocenter has opposite configuration. We could do the pancake flip operation to this one to the side, and you can see more clearly that they are mirror images of each other. Shortcut for things that are enantiomers: if two molecules each have one stereocenter, if they're stereoisomers of each other and they only have one stereocenter, and those stereocenters have opposite configuration, they have to be enantiomers. Okay? Diastereomer is the catch-all term for anything that's not an enantiomer. Okay, and then some of you may be uncomfortable with the fact that we've got a positively charged oxonium ion as our product. Water here is not only our nucleophile, it is likely our solvent. There's tons of water around, so what probably happens next is water removes the proton from our product. This seems reasonable because the pKa of a positively charged oxygen with a proton on it is around -2. So you'd predict a fairly reasonable equilibrium constant for removing the proton from our alcohol to get H3O+. And you would predict, because we've got so much water here, that this is easy to get as products. So if I were, which are products, I would need to draw two of these. I would need to draw both enantiomers as products of this reaction. Yeah?
Can you explain one more time what SN1 means?
Yep. SN1 means this stepwise mechanism where we break the carbon-leaving group bond first, and then the nucleophile comes in and attacks the carbocation. S stands for substitution, because in the reaction we have substituted CN for I. It's N for nucleophilic, because we got a nucleophile involved, and 1 is there's only one molecule in the rate determining step. Unimolecular nucleophilic substitution. Yes?
Could you have a molecule that performs both SN1 and SN2 reactions as you can have multiple groups on a molecule?
Could you have a reaction that's somewhere between SN1 and SN2? Yes, but we're gonna pretend that world doesn't exist. But let me show you sort of how you would tell that was happening. Notice that for this SN1 reaction, we start with something that is chiral and optically active. We end up with a mixture of enantiomers. And can there be any excess of one enantiomer over the other here? Not if you have a full carbocation intermediate, because the faces of that carbocation are totally symmetric, and therefore you can't prefer one over the other. So what we would get here is a racemate, or a racemic mixture, a 1-to-1 mixture of enantiomers. So we will have lost optical activity. So one way you can tell that a reaction has SN1, that the mechanism is SN1, is if you start with a chiral starting material where the stereocenter is at the leaving group, but in the product you've got a 1-to-1 mixture of enantiomers. That's a dead giveaway for an SN1 reaction. Let's talk about, any questions you want to ask about that? Yeah?
You said you start with a chiral molecule and the leaving group is
At a stereocenter. Right. If your molecule is chiral and the leaving group is at a stereocenter, and you go through a non-chiral or achiral intermediate, you cannot favor one face of that intermediate over the other. They have to be attacked at similar rates, identical rates, and you have to get a one-to-one mixture of enantiomers. So stereochemistry can be evidence of reaction mechanism. If you lose optical activity in a reaction, chances are you went through an intermediate that was not chiral, and you lost your stereocenter, you lost your stereochemistry in that intermediate. Okay? Other questions about that? Yeah.
So, is there any way with any catalyst or some kind of thing to make only one of those enantiomers?
Is there a way with a catalyst to make only one of those enantiomers? Yes, sort of. I guess a general principle in OCHEM that applies more than just in this situation is that if your starting materials are not chiral, and or if you go through an intermediate that is not chiral, and you make a stereocenter, you got to make both varieties. Now, if you use a chiral catalyst, all bets are off, and you can prefer one enantiomer over the other. Yeah?
So with the nucleophilic attack here at the pi orbital, I guess maybe I'm thinking of it wrong, but so that pi orbital, doesn't that represent like, so it's positive sign and negative sign for the function. Wouldn't one electron go in each so that they're opposite spin? Like,
okay, right. So let's see. The sign of the wave function actually has nothing to do with spin. That's a different thing entirely. So, and this is a 2-electron reaction, meaning the 2 electrons at lone pair on water dump their electron density into the p orbital. It's simultaneously on both sides, and so it's just an issue of which side you choose, and one side is not favored for another over the other.
so you're saying both electrons are spread over the entire.
Well, so in this intermediate that's positively charged, there are no electrons in that empty p orbital. But if there were, they would be spread over the whole thing.
So we have to draw both enantiomers
Because you can attack from either side. You can attack the same orbital from either side. Okay, yeah?
I mean, this is pretty common. We see this a lot with racemates.
So is this kind of thing pretty common? This is yes, one way you can get a racemate. If you go through a not chiral intermediate or your starting material is not chiral. All right, let's do the same reaction. We're going to alter the players just a little bit to alter the mechanism. Let's do the same basic reaction, same starting material, but let's choose this SN2 mechanism. And let's see, here is the stereocenter with the bromide. Instead of water, we're going to use hydroxide. We're going to talk about this, but it should be pretty easy to tell that hydroxide is a better nucleophile than water. And the way you can tell that is to compare the pKa's of their conjugate acids. For hydroxide, the conjugate acid in water, pKa 16. For water, the conjugate acid is H3O plus, pKa minus 2. So the stronger base has the less acidic conjugate acid. This is a stronger nucleophile. Now, let's talk about how this reaction might happen. All we know so far, based on the kinetic experiments, is that both starting materials are involved in the rate determining step, and we're going to be forming the carbon bond or the carbon nucleophile bond at the same time as the leaving group is leaving. So you might envision, and we could just draw something like this. But the question is, which of the two products do we get? And let me show you why you might expect, how you might get either one, and then why one of them, I'll tell you, one of them is preferred over the other. So let's look at the transition state for this reaction. And to do this, it might be useful for us to redraw this stereocenter a little bit differently. I'm kind of struggling here. Oh well. I think that's right. No, it's exactly backwards. Okay. So you can imagine two possibilities for a transition state. One in which the nucleophile comes in from behind the breaking carbon bromide bond. We will call that backside attack. And we would draw a transition state that looks something like this, where bromide is leaving and OH minus is coming in. And the product that came from that transition state would end up with the OH replacing the Br, but notice that the OH ends up on the opposite side. And one way you can show that from this perspective, would be like this. Okay? Option 2 would be front side attack, and this would involve the nucleophile coming in let's suppose the carbon bromide bond is breaking and then the carbon oxygen bond is being made. Here's a transition state. And if this were operative, if this were the one that's going on, then you would predict that you would install the OH group on the same side as the bromo originally was. Okay? But notice that at no point, and one way to draw this would just be to show this is the product. But notice there are, because the bonds are forming and breaking at the same time, there is no transition state we can draw where we lose stereochemistry, where we go through a non-chiral, where we go through a non-chiral intermediate. So we would predict, if the reaction is concerted, that we're not, is SN2, that we're not going to lose optical activity. Now, option 1 is preferred here. Backside attack is preferred for the SN2 reaction. And there's a few reasons for that, but let's sort of talk about why that might be. Why do you think that option is preferred? Yeah.
Less interference from electron repulsion?
Yeah, less interference from electron repulsion. Very good. So you have the nucleophile, which has a partial negative charge, and the leaving group with a partial negative charge. And they are as far apart from each other as possible. So you're minimizing electron-electron repulsion. Good. What else? Yeah?
Better bond angles.
Better bond angles? Okay, yeah. I think if you were to do the valence shell electron pair repulsion thing, you probably got some non-ideal bond angles for this second option. There's another explanation that has to do, go ahead.
Is it reduced stereochemistry?
Reduce steric hindrance. Yeah, that's a great way to summarize the idea that we're minimizing electron-electron repulsion, we're keeping the nucleophile and the leaving group as far apart as possible, and we're avoiding undesired bond angles. Tell me about this. Oh yeah, sorry, go ahead.
The sigma antibonding, like the large lobe is pointing away from the carbon bromide bond.
Ah, very good. So here is the node. If we draw the carbon bromide sigma star, it's going to look something like this, with tiny lobes in the middle and large lobes facing outward from the bond. We know that we're going to attack carbon. I mean, this was actually an exam problem. It's more reasonable to attack carbon than it is to attack bromide, because having Br minus as the leaving group is a lot better than having a negatively charged carbon as the leaving group. But yeah, backside attack is preferred because that's where most of the sigma star is. Okay, and maybe you could have actually predicted that based on your HOMO-LUMO intuition. This is one reason why we spent so much time on HOMO and LUMO, because now you don't need to memorize that the SN2 reaction proceeds via backside attack with inversion of stereochemical configuration, because that just falls out of the mechanism if you understand where the HOMO and the LUMO are. Do you see how this is consistent with the orbital picture? Nucleophile, lone non-bonding lone pair electrons on oxygen attack the carbon bromide sigma star at carbon from the backside. In a single step, we break the carbon bromide bond, we make a new oxygen carbon bond, and there's a switch in stereochemical configuration because the carbon sort of inverts or goes through, does the umbrella turning inside out sort of thing. All right, well, I got a couple minutes left, but I'm sick of talking, so have a happy President's Day. I'll see you, I think, on Tuesday, which is Pretend Monday. All right.